Hi, and welcome back to Mastering Anesthesia. Have you ever wondered what happens in 0.8 seconds? The universe expands by approximately 1.6 million kilometers. Light travels nearly 240,000 kilometers. And inside your body, something remarkable is taking place. That's right. Your heart beats in 0.8 seconds. That's how long it takes to complete one cardiac cycle. Stay tuned till the end of this video as we study the different phases and events taking place in cardiac cycle. This is Mastering Anesthesia, and let's go.
What is the cardiac cycle? Well, the cardiac cycle refers to the complete sequence of physiological events that occur in the heart from the beginning of one heartbeat to the beginning of the next heartbeat. The cardiac cycle has two distinct phases, the diastolic phase and the systolic phase. The diastolic phase is when the heart relaxes. It is very important, thereby giving it 4 steps. This is when the heart is filled with blood. The systolic phase is the contraction part of the cardiac cycle, and it expels blood from the heart to the systemic or the pulmonary circulation. It has only 2 steps in the systolic phase. For the diastolic phase, the first step is the isovolumetric relaxation, followed by rapid ventricular filling, then slow ventricular filling, and then is the atrial contraction. As for the systolic phase, it has isovolumetric contraction, followed by ejection. It is fairly easy to remember the diastolic phase's steps and the systolic phase steps. Just remember the diastolic phase has 4 steps, systolic phase has 2 steps. Both of these phases will start with isovolumetric, either relaxation or contraction. So for the diastolic phase, after it relaxes, followed by rapid ventricular filling and then slow ventricular filling, and then finished off by atrial contraction. And we go to the systolic phase. It always starts with isovolumetric contraction, since this is the systolic phase, and then ejection of blood into the circulation. Now let's talk about the events making up the cardiac cycle, as in what particularly happens in each of the steps in the phases of cardiac cycle. It has traditionally been agreed upon that cardiac cycle starts from late diastole, which is the second half of the diastolic phase, where the atria and ventricles are both relaxed and the AV valves are open. Therefore, cardiac cycle starts from slow ventricular filling, atrial contraction, then goes into systolic phase where it continues into isovolumetric contraction, ejection, isovolumetric relaxation, and last step of the cardiac cycle would be the rapid ventricular filling. What happens in slow ventricular filling is that pressure in the atria will be slightly higher than the pressure in the ventricles. This will cause the AV valve to open, thus allowing blood from the atria to flow into the ventricles. This is reflected as this flat part of the curve or slightly increasing left ventricular pressure time curve. Next step in the cardiac cycle is the atrial contraction. It starts off with pacemaker cells from the SA node generating action potential when it polarizes. It conducts to the atria, causing atrial contraction. This will cause the remaining blood in the atria to be ejected into the ventricles. This is known as the atrial kick. And a very important note, at rest, this atrial kick contributes to only 10% of ventricular filling, and the remaining 90% is through passive filling. But its role comes into more significance during exercise, where the atrial kick contributes to almost 40% of the ventricular filling. Atrial contraction will start with the P wave, reflecting the depolarization of the atria. On the venous waveform, this will be reflected as the A wave, where the pressure generated during atrial contraction is transmitted along the vena cava and pulmonary veins, as they have no valves. Left ventricular pressure curve also has a positive deflection, showing that the pressure slightly increases during atrial contraction. You can see it in the heart when the atrial contracts, causing this atrial kick rapidly empties the atria from its remaining blood into the ventricle. Therefore, at the end of atrial contraction, we are at the end of the diastolic phase. Therefore, the volume of blood in the ventricles at the end of this phase is the end diastolic volume, typically around 120 mL for a healthy 70 kg man. For the next step of the cardiac cycle, we've already entered into the systolic phase, the isovolumetric contraction, where the pressure increases but the volume remains the same. So that is why it is called isovolumetric contraction. It starts off by the continuation of the action potential from the SA node to the AV node, later on to the His Purkinje fibers represented on the ECG as the QRS complex. This causes ventricular contraction. When ventricles contract, the pressure in the ventricles will exceed the pressure in the atrium. This will cause the AV valve to close. Closure of the AV valve for the left ventricle, the mitral valve, will cause the S1 sound, represented by this squiggly line on the heart sound right when the mitral valve closes. At this point, both the AV valves and the semilunar valves are both closed, represented on the graph by this highlighted portion. This is where isovolumetric contraction happens because all the valves are closed. The volume will not change, but the pressure will increase significantly, and the blood cannot go anywhere because all the valves are closed. On the graph, you will see this dramatic rise in pressure from one highlighted end to the next highlighted end, representing isovolumetric contraction. This highlighted portion is very important because each of the beginning and the end resembles the opening or closure of some valves. This is where the mitral valve closes, valve open, valve is closed, and the valve is open. I will go into the specifics at the end of the video. Now what about venous waveform? During isovolumetric contraction, there will be increased in the right ventricular pressure during contraction. The tricuspid valve will bulge into the right atrium. This causes an increase in the pressure in the right atrium. This corresponds with the C wave. Remember it as contraction. Here's the C wave on the venous waveform on the overall cardiac cycle graph. Now we've come to the ejection part of the systolic phase. Ejection happens when the ventricular pressure exceeds pressure in the pulmonary artery and the aorta. When that happens, the semilunar valves will open, which is the aortic and pulmonary valve, causing the blood to be ejected from the ventricles into the aorta and pulmonary arteries. It is interesting to point out here that the flow of blood through the semilunar valves are initially rapid, then it slows down. This can be seen on the left ventricular pressure curve, where the first part is initially incrementing the pressure and then the pressure subsides. This happens due to myocyte repolarization. Then what about the venous waveform happening here in the ejection phase? When the right ventricle contracts, it will pull the tricuspid valve downwards. This will in turn causes the lengthening of the right atrium. When the length of the right atrium increases, the pressure will subsequently drop. This is seen on the venous waveform as the X descent. When the pressure is reduced, the volume of blood will fill the atrium. Here you can see the X descent represented on the overall graph. Now in the course of ventricular relaxation, depicted on the graph there, the pressure of the ventricles will fall below the pressure of the aorta and the pressure in the pulmonary arteries. Now let's see that on the diagram of the heart. Here depicted is the pressure of the aorta and pulmonary arteries being greater than the pressure in the ventricles. When this happens, the semilunar valve will be forced to close. Here in the initial portion of the highlighted part is the part where the aortic valve closes. When it closes, it will cause the second heart sound, or S2, depicted also on the graph by this second squiggly line corresponding with the aortic valve closure. You can see here that The ejection phase of the systolic phase is bounded by when the aortic valve opens and when the aortic valve closes. Another interesting event happening here can be seen on the aortic pressure curve. Here, when the aortic valve closes, it is represented on the aortic pressure curve by the dichrotic notch. It is a positive deflection caused by the elastic recoil of the aortic valve and the aorta. After completing ejection, we are done with the systolic phase or the contraction phase of the heart. Therefore, any remaining blood in the heart ventricle is the end systolic volume. It is typically taken around 50 mL for a healthy 70 kg male. By knowing these facts, we can calculate the stroke volume, which is the volume of blood ejection from the left ventricle per heartbeat. The volume of blood in the left ventricle prior to contraction is the left ventricular and diastolic volume that we've discussed earlier, and the volume of blood remaining in the left ventricle after contraction is the left ventricular and systolic volume, which is what we got here. Therefore, if we minus left ventricular and diastolic volume of about 120 mils just now, with the left ventricular and systolic volume of 50 mils, we will get a stroke volume of 70 mils. Now let's talk about isovolumetric relaxation. We've now come back into the diastolic phase of the cardiac cycle. Isovolumetric relaxation happens in this highlighted portion of the cardiac cycle. It is bounded by the aortic valve closure and when the mitral valves open. It will take a short while before the ventricle's pressure to fall below that of the atria. Therefore, at this stage, the pressure will fall, but the volume will remain the same because all the valves are closed, so blood is not flowing anywhere. In the venous waveform, on the other hand, the atrial pressure slowly rises as venous return from the lungs and vena cava. V stands for venous return. That's how I remember it. As for the left ventricular pressure, there will be this steep downward deflection of the isovolumetric relaxation. Next comes the rapid ventricular filling. Once atrial pressure exceeds ventricular pressure, the AV valves will start to open. And when the AV valves open, blood will flow down its pressure gradient from the atria to the ventricles. In the initial phase of diastole, the ventricles are still relaxing. Therefore, intraventricular pressure continues to decrease like so, causing the blood from the atria to flow rapidly into the ventricles, so that it's called the rapid ventricular filling. As for the venous waveform, the decrease in the atrial pressure is represented by the Y descent, like so on the venous waveform. Now that we have completed all the two phases of the cardiac cycle, let's practice how to draw the cardiac cycle pressure time curve. Start by drawing two axes, the x-axis and the y-axis. The x-axis will represent pressure in millimeters of mercury, and y for time in seconds. As for the pressure, we will put a range of 0 to 120 millimeters of mercury, and 0 to 1 second for the time y-axis. Let's start off with the left ventricular pressure curve. It starts off with this flat part of the curve, followed by a positive deflection showing slow ventricular filling and then atrial contraction. Remember that cardiac cycle starts off with the late part of diastole, followed by systole, and then the first part of the diastole. Then the pressure in the ventricles will exceed pressure in the atria, causing the mitral valve to close. This will cause isovolumetric contraction, where the pressure will suddenly rise, and all of this is bound within this highlighted portion, the isovolumetric contraction, where all valves are closed. And the ventricular pressure exceeds the pressure in the aorta and the pulmonary arteries. The aortic valve opens, therefore the ejection phase ensues, so the blood is ejected into the aorta and pulmonary arteries. So the graph is deflected positively and then it subsides due to the relaxation following ventricular contraction. Ventricles will continue to relax. When the ventricular pressure is less than aorta and pulmonary arteries, the semilunar valves will close. here depicted as aortic valve closes. So pressure will continue to fall in this isovolumetric relaxation bounded in this highlighted portion where all the valves are closed, and pressure continues to fall but the volume remains the same, therefore isovolumetric relaxation. Mitral valve opens here when the pressure in the atria exceeds pressure in the ventricle, and since the ventricles are still relaxing, the intraventricular pressure will continue to fall as depicted on the left ventricular pressure. As for the aortic pressure curve, the graph starts from mid-diastole, so the graph starts from anywhere below 120 until it reaches the point where the aortic valve starts to open. When blood is ejected from the ventricles into the aorta, the aortic pressure will rise dramatically and then falls when it relaxes. And when the pressure falls below that of ventricles, the aortic valve will close. And remember, in aortic pressure, there is this dicrotic notch contributed by the elastic recoil of the aorta and aortic valve when it closes. As for the right atrial pressure curve, it starts off with the A wave, depicting atrial contraction, followed by the C wave when the tricuspid valve bulges into the right atrium following right ventricular contraction. Then the X descent is when the right ventricle contracts and pulling the tricuspid valve downwards, lengthening the right atria length, causing the pressure to fall. The V wave happens because of the venous filling of the right atrium. And when the mitral valves open, atria will empty its blood into the ventricles, reducing the pressure, and this is depicted as the Y descent on the right atrial pressure venous waveform. As for the ECG, the P wave will precede atrial contraction. The R wave corresponds with the beginning of ventricular contraction or systole, and then the T waves is the ventricular repolarization, happens just before ventricular relaxation. Last but not least is the heart sounds. You have S1 occurring at the closure of AV valve at the beginning of isovolumetric contraction, here at the highlighted part, and S2 happens at the closure of a semilunar valve at the start of isovolumetric relaxation, here at the highlighted portion of the beginning of diastole.
Thank you for watching. If you find these videos helpful, please hit the like and subscribe button to show your support. Comment down below what topic you want us to cover next. Till next time, see you in the next video.